So welcome to the last session of the day. This is going to be the hands-on on Wannier functions that is going to be led by Antimo Marrazzo from University of Trieste and Junfeng Qiao from EPFL, titled Maximally Localized Wannier Functions using Wannier90. Antimo, Junfeng, please. Stage is yours.
Thank you, Andrea. So let me just fix this below here. Can you see the slides?
Yes.
Okay,
yes.
Fantastic. So thanks, Andrea, for introduction. So indeed, now we will move closer to the code, close to actual calculation. So Giovanni gave a very nice introduction to the theory of maximum localized Wannier functions, to the technical aspects and the mathematics. And at the very end, he mentioned as well the fact that you actually need a code to compute this. And so now we will move closer to this code, which is Wannier90, and see how you can actually compute yourself Wannier functions. Okay, so I will give a short introduction to the tutorial, give you a little bit of information about Wannier90, how it works, and some crucial aspects. And while Junfeng will actually will run the tutorial for you, we'll show you how you can run the exercises, and I will stop, maybe we'll stop him at some point to read to loud or some of the most general questions you will ask on Slack. Okay, so we will talk mostly about Wannier interpolation. Giovanni mentioned you can do many different things with Wannier functions, but today we will focus on Wannier interpolation because that's the feature that is more relevant for this school, for this workshop. And I will, as I said, I will give you the basics of Wannier90, but given that there are many of you here today attending this webinar, I will also give you some more advanced concepts that might appeal to those of you who are already experienced with at least the basic features of Wannier90 and Wannierization. Okay, so Wannier90 as a code, it has been around for quite some time, but I think the modern way to look at this code is to look at a package that is at the center of a much wider and broader software ecosystem. Okay, and it's a little bit like an interface between ab initio engines on one side. So we have codes, DFT codes like Quantum Espresso. We have codes like GPO, VASP, PySCF, FLIR, you name it. We have interfaces with very, very many different ab initio codes. And on the other side of this interface, there are many materials properties you can actually compute thanks to Wannier function, and especially thanks to interpolation. Okay, so we go from simple band structure calculations and interpolation of band structures and band velocities to transport codes, to DMFT codes, to the interpolation of electron phonon coupling. And in many of these cases, the properties that you can compute, these materials properties, they can actually be computed just because Wannier interpolation exists, just because you can leverage this powerful accelerator. Otherwise, it would be too computationally too intensive to actually compute them directly. So I will not repeat the theory of Wannier function. I'll just give you 2 slides to summarize a bit what Giovanni said in the last talk. So we start from an electronic ground state calculation. It's a first principle simulation. In this workshop, we use Quantum Espresso. And then we want to compute Wannier functions. And we do this by what is called a subspace selection and a unitary transformation of block wave function. I think this equation here at the center of the slide is probably the most important equation, in the theory of Wannier functions. So you have your block states, you rotate them with a unitary matrix, and then you Fourier transform, and you get your Wannier functions. In order to get Wannier functions that are maximally localized, okay, you need to choose this and k in a specific way, and in particular, you need to minimize what is called the spread function of this omega object that you see here. So you start with the sort of delocalized block wave function, and you end up with a Wannier function, which is a localized object in real space. In practice, this is all about minimizing the spread functional. You have a gauge invariant part, as Giovanni mentioned, that not much you can do about it, especially for composite bands. But then there is a gauge-dependent part, and that's what you can minimize by optimizing your unitary matrices. In practice, this means following the gradient. Okay, it's an iterative minimization procedure. Somebody asked me in the chat in the previous talk while Giovanni was speaking, if you just need the overlap matrices. Yes, you just need these overlap matrices. But in practice, one needs, and this is critical for disentanglement, but in practice, it's also needed for composite bands to specify an initial subspace and an initial gauge. And so the way we do this is through this AMNK projection matrix, okay? So it's another matrix you need to Wannierize, which is typically, and this was the typical case until very few years ago, is typically constructed by considering a set of localized projection function, okay? Namely orbitals like S orbitals, P orbitals, D orbitals, sp3, sp2, you can have hybrid orbitals, and you can center them wherever you want. Of course, this choice is arbitrary, but it needs to make sense, and this is where the experience comes in. But as Giovanni has mentioned, these days there are other options, and in particular there is this SCDM method that we will not discuss today, but it's good that you know that it exists and it's freely available in the latest version of the code, where you don't need to think too much about the chemistry of your problem, but you just turn on a flag and you employ this SCDM method, which is based essentially on linear algebra operations, okay? So you need these overlap matrices, M and K, you need this projection matrix, AM and K, and then you can Wannierize. And the way you do it, I mean, probably the most popular way to do it is to use Wannier90, which is a Fortran code. It's written in Fortran 90, modern Fortran. It's open source. You find it online. This is the reference website, wannier90.org. You can find the latest version of the code. It's very light. It's much lighter than Quantum Espresso. It's a much smaller code and much simpler to use and to understand. These days, there is also a GitHub web page, the Wannier90, where you can also find all the versions of the code, actually, not just the most recent one. And I really recommend you to use this website because it contains a lot of useful information, okay? Even if you are an experienced user, okay? There is a user guide, which is extremely well done, where you find an explanation of all the input variables of Wannier90. And then there is an extensive set of tutorials. I think we have more than 30, if I'm not wrong. And for many of these tutorials, we have solutions, okay? So there are solutions that explain all this. The tutorials explain themselves the steps, but the solutions show you what the right results. And these tutorials are designed in a way that they cover most, if not all, the functionalities that are available in Wannier90. There is a community of people developing and using Wannier90, so you can subscribe to the mailing list of this community. It's very low traffic, few emails per month, so I mean, really it's recommended. And then, of course, there is also a reference publication that explains the methods that are implemented by Wannier90, all the features of the code, and how to use it. And it's important that you cite this also because it's a way to acknowledge all the work of the people developing the code. And as you see, there is actually a large number of people involved, and this is something that I want to stress, as Giovanni has already mentioned. The code was initially an effort by Nicola Mazzari, Ivo Sousa, and David Vanderbilt, in the late 90s, but that was just the start of a very, very successful enterprise. The people like Arash Mustafa and Jonathan Yates rewrote the code, made it robust and available in modern Fortran. But then more and more people started to join the community. Giovanni Pizzi was a key figure for many years. More recently, also Valerio Vitale. And we came to the point where beyond this group of core developers, there is now an entire community, as I said, of people actively developing the code. And you see there is a long list of authors in the most recent paper. But this is actually, I think, a growing list. So there's more and more people getting involved into this code. And one of the reasons is because, as I mentioned in my first slide, Wannier90 is a bit like a door that gives you access to many materials properties. Okay, so there are many people coming from different sub-communities in electronic structure that are interested to develop functionalities within Wannier90 and around Wannier90. So it's a community-driven code. Okay, we use a GitHub model. We develop things there, and you can actually be part of this community. You can be a contributor. You can at different levels. You can be a developer if you wish, but you can also simply report bugs and hopefully fixes for those bugs, and implement new features and contribute them to the main code. And this is of course very welcome, and we really sort of are open to external contributions to the code. The code has many features. I will not review all of them. I will just focus a little bit on what are the most relatively recent and new features. Of course, it's a code that can produce maximally Wannier function. It contains the Marrazzo Qiao scheme. You can do disentanglement. That's, I would say, the basics. But you can do even more sophisticated things like symmetry adaptive Wannier functions. Okay, so where you obtain Wannier functions, but those are not necessarily maximally localized. There are symmetry constraints, and there are a number of different techniques to have more symmetric wave functions. Okay, I will not discuss this topic today, but it's something that might be interesting for a number of you. As I mentioned, there is this new SDM method to get initial projections. Okay, so this is something that is implemented and freely available. Everything works with spinor wave functions, so you can do spin-orbit Kaplan calculations. You can interpolate a number of quantities like Hamiltonian for band structure calculation, but also other quantities. I want to mention that the code that recently has been parallelized, so it uses MPI parallelizations, and this is very useful to speed up the calculation. As I said, one of the most popular and common use case is interpolation, and you can interpolate a number of different things. You can interpolate density of states, band structures, projected density of states. But you can also interpolate more sophisticated quantities like Berry phase properties, going from the Berry curvature to orbital ionization and other even more complex objects. And there is a lot of code dedicated to transport, from ballistic to Boltzmann transport in the relaxation time approximation. You have Seebeck coefficients. We have even the spin-hole conductivity has been added recently, okay? And there is more than this, actually. Among all these things, one that is particularly relevant, and I will come back to this aspect in one of my last slides, is the interpolation of GW band structure. Because, one of the reasons why in this workshop about Hubbard corrections and the DFT plus U and Koopmans, one of the reasons why we have so much time devoted to Wannier functions, because it's those techniques, they particularly benefit from interpolation. And in particular, I want to mention that there is a dedicated feature for GW interpolation of Wannier interpolation of GW band structure, but we'll come to that in a moment. So talking about interpolation, this is a bit for those of you who are maybe a little bit more experienced with Wannier90 and want to know some more recent advancements. Giovanni has mentioned that you can use this idea of Fourier transform, of Fourier interpolation, doing calculation, electronic structure calculation like DFT on a coarse grid in reciprocal space. Fourier transforming in a real space, so you write things in a basis of maximally localized Wannier function that are exponentially decay. So it's it's a particularly efficient way to represent your quantities, like your Hamiltonian, for instance, in this case. And then you Fourier transform back to interpolate in this case, your band structure, but it can be other quantities to reciprocal space. Okay. And this is, Giovanni has mentioned it. It's very similar to what happens in signal processing. It's the famous Nyquist channel condition. As long as your sampling rate, your signal has a finite bandwidth, and your sampling rate is at least twice the bandwidth, you can reconstruct the signal from a finite sampling. Okay, so this is what we are going to do. We will Wannierize the system, write your Hamiltonian in real space in a basis of Wannier functions, and then Fourier transform that matrix to reciprocal space and just diagonalize this Hamiltonian. Okay. A technical point that I want to mention that has been implemented recently in the code is that if you do it naively, so if you just consider this summation here to run on the Bonfort-Karman supercell, just on the capital R vectors, it's not the most correct way to proceed. What is actually the right thing to do is to consider the Wigner size supercell, or in simpler terms, to account that if you want to calculate the hopping, let's say all the matrix elements between Wannier function A and Wannier function B that are sort of certain distance apart from each other, the closest Wannier function B might not be the one that you find in the Bonfort-Karman cell, but it might be one that sits in one of these periodic replicas. Okay, so it might be one of the periodic replicas, so it might sit in one of the neighboring Bonfort-Karma supercell. Okay, and so this is equivalent to consider the Wigner-size supercell instead of the Bonfort-Karma supercell. So the formula to interpolate quantities is slightly more complicated. You see there is an additional summation over these T vectors that are the direct lattice vector of these Bonfort-Karma supercells. But it has a very practical consequence. So first of all, you can interpolate things by just sampling at gamma. Okay, this is if you use the first naive formula at gamma, you would just interpolate flat band structure, which is of course wrong. So it's the clearest example is really the gamma only case. But even for finite k-points grid, by using this more slightly more complex formula, you can get much better, much more accurate band structure. And this means that either you improve your accuracy for a fixed k-point grid, or you can use a much cheaper and coarser k-point grid to get the same accuracy in the interpolation. Okay, you see this, the orange lines are the new sort of current implementation, and the blue one is the old implementation. Okay, so this is a technical aspect to keep in mind, but it's really what is implemented in the code. It's really what you should do. Okay, we have seen a bit some general concepts about the code. The fact that it's open source, so you can download them online. How is this structure? The features. But now let's see how in practice you calculate this Wannier function. We said that you need overlap matrices, this MM and K, between neighboring K points, but you also need projection matrices. Okay. This is AM and K matrices. In practice, often you need other inputs. The minimum input, if you want to do band structure interpolation, is the list of Hamiltonian eigenvalues. Okay, there is a file that is produced, that just contains eigenvalues at each K point. That's for interpolation. If you want to plot Wannier function, you need to also produce the orbitals, the U and K orbitals in real space. But I want to stress that this is only for plotting Wannier function. If you want to just interpolate band structure, you don't need the block orbitals. Okay, that's not necessary. And given that Wannier90 can actually compute very complex properties, sometimes you need optional matrices that are more, beyond what we have seen up to now. So spin components or matrices like the UHU or UIU, where H and I are the Hamiltonian and identity matrices, and U are the block orbitals at different K points. So you can have different inputs, but the minimum is MM and the overlap matrix and the projection matrix. And these inputs can be obtained with different programs. Today we will focus on Quantum Espresso. Okay, but just keep in mind that you can do this also with VASP or other codes. How do you do this in practice? Okay, you need to produce these matrices. You need to get the MMN. And you need to do it starting from electronic structure calculation. So we use Quantum Espresso. So we do an self-consistent calculation with pw.x. Okay, we get a ground state charge density, and that's done on a irreducible Brillouin zone. So on a converged K-point mesh in the irreducible Brillouin zone. After that, we do a non-self-consistent calculation. That is done typically on a different K-point grid. And it needs to be a uniform complete grid. So now we work with a full Brillouin zone. We do not exploit symmetries, okay? There have been some recent developments about this, but this is still sort of work in progress. But the standard way is to just calculate things on a uniform grid. And then you use Wannier90 to produce an input file for the interface program, okay? Because we said that Wannier90 sits at the interface between properties and ab initio engines. And so different ab initio engines are connected with Wannier90 with their own interface program. In the case of Quantum Espresso, this program is called PW to Wannier90. You find it inside the Quantum Espresso package. And the input file for this PW to Wannier90 is produced by Wannier90 itself. You produce it with Wannier90 minus PP with this pre-processing flag. And this interface program, if you run the program, it takes care of getting the wave function from the NSCF step and producing all these matrices that you need to run Wannier90. So the overlap matrix, MMN, the projection matrix, AMN, the eigenvalues list, and so on and so forth. And finally, you run Wannier90, okay? Wannier90 reads this MMN, MN, and IG and other files and minimizes the spread function, gives you the Wannier function, interpolates the band structure, calculates transfer properties, and depending on what you want the code to do. Of course, if you do a DFT calculation, you can still do band structures the usual way, so the direct calculation, and so you would do a bands calculation, an SCF, or an NCF. I think you have seen this maybe in the earlier tutorial this morning or early this afternoon. And then you do a bands.x and a plot band.x calculation. That's the usual way. But if you want to, and you can use, for instance, that to check the quality of your interpolation to see if your interpolation is reasonable. But if you want to do that, this is a practical tip, please do it in a different folder. So do not mix the two paths. Just do all the Wannierization in one folder and all the standard best calculation in a different folder. This is otherwise you mix the temporal for quantum espresso and you get weird results. Okay, so Junfeng will show you 3 exercises, okay, where that sort of guide you through these features. The first 2 exercises are about silicon. In particular, the first exercise will teach you how to produce Wannier functions, maximally Wannier function for the valence bands of silicon, okay. And in the exercise number 2, you will see how to do valence band plus some conduction bands of silicon by using the disentanglement method, okay? You will check the results, see if they're sort of good, if they're consistent, analyze the output of Wannier90, and also you will learn how to plot the real space Wannier functions by using software like Xkristen or Vesta, and look at the shape, of this isosurface of this Wannier function. And finally, also plot, of course, the band structure that you interpolate with Wannier90 and compare it with the ab initio calculation. So I will not really rediscuss the input file quantum espresso. This is just a very quick sort of refresh. This is a typical SCF input file. You specify the type of calculation, where the potential are, describe the system, number of atoms, pieces, some parameters for the diagonalization, like thresholds for charge density calculations, the atomic positions, k-points grid, which is particularly important in our case because it's what defines the grid used by Wannier90. But these days, and I think this has also been mentioned this morning, you don't need to start from scratch necessarily. You can use tools, web tools like this Quantum Espresso input generator that you find at the Materials Cloud, where starting from a crystal structure that you give as an input, this web application gives you an input file for Quantum Espresso that follows and is compliant with a specific protocol that you select. Okay, this doesn't mean that you can stop doing your convergent test, but at least it's a good starting point. If you want to study a novel material that you never sort of met before. And of course, this has many functionalities. You can also visualize the structures and do different things. Now let's move instead to the input file of Wannier90, which is actually much simpler, you will see, than the input file of Quantum Espresso. This input file has always an extension that is .win, okay? And when you run the code, you don't need to specify the full file, you just specify the base name, okay? So if your input file is exercise1.win, you just specify exercise1. And if you want to run the Wannier90 code as a preprocessor to produce the input file for PW to Wannier90, you add this -pp preprocessing flag. Otherwise, you just run it as it is, Wannier90.x, and then the base name. The input file format is very simple. There are no name lists, okay? It's just variables equal to something. So you have number of Wannier functions, in this case, equal to 4, Moncor SPAC grid equal to 6 by 6 by 6. There are blocks, and this is especially useful, this blocks format for positions of atoms, coordinates of atomic coordinates, but also lattice constants and specification of projections. Okay, units. The default units are angstrom, but Bohr are also accepted if you specify that, and energies are eV. This is an example of an input file you will encounter in exercise 1. You see that you need to specify the number of bands. This needs to be equal to the number of bands you have in the NSF calculations, unless you specifically exclude certain bands. There is an option to exclude from some bands from among the ones you computed with Quantum Espresso. There is a number of Wannier functions that you need to specify. Then you have a number of iterations in the maximally localization procedure. You can restart. So an interesting feature of Wannier90 is it actually allows checkpoints. So you can, if you Wannierize your system, you just want to reinterpolate the structure or revisualize, replot the Wannier function. You don't need to go through again, all the Wannierization procedure, all the minimization. You can just restart from the plotting sort of part of the code. So you can plot Wannier functions and specify in which supercell you want to plot them. You can write interpolated instruction. This is done by the bands_plot flag. You need to specify, of course, a k-point path, which is what is done here. And there are optional flags also to specify how many k-points you want to use in the sampling of this path. Of course, a core part of the input file is the projection block, where you need to specify your projection. In this case, you have 4 s orbitals centered in these points where that are specified by fractional coordinates. If you look at the user guide, there is an extensive explanation of all the different ways you can specify projection. There are many different ways, by just saying I want p orbitals to silicon, to specifying precisely, an arbitrary point in space, an arbitrary shaped atomic orbital, and there are many options that I recommend you to go through. You need to specify the k-point grid and explicitly list the k-points that you use. And then, of course, you need to say where the atoms are and how the unit cell is done. And this was the sort of, way to highlight the different things. Okay, so the final exercise number 3, is about the band structure interpolation of a different material, which is called lead. So it's, again, a very simple crystal, but it will show you how, at least a less trivial case where you need to specify projection. You will see how to specify d orbitals, for instance, or sp3 orbitals, okay? But the most important part of exercise 3 is actually the Fermi surface interpolation, which is one of the most useful features of Wannier interpolation and Wannier90 in general, okay? So it's clear that if you want to interpolate band structure, you can benefit from a Wannier representation and Fourier transform. But in the case of Fermi surface, this is even more evident, okay? So suppose you want to do a decent Fermi surface calculation of lead, you would need to calculate something like 50 to the third k points, okay? That would be more than 100,000 k points, which is, of course, extremely expensive to do if you need to do it with a direct calculation by diagonalizing the full DFT Hamiltonian at all of these k points. While with Wannier interpolation, this becomes almost trivial. So it's extremely efficient to compute. It's an extremely efficient method to compute this Fermi surface, because once you have your Wannier Hamiltonian real space, you can afford to calculate this on really, really absolutely very dense k-point grid and construct a very, very fine Fermi surface in the reciprocal space. And we will see this in exercise number 3. So before I conclude, I want to mention, to go back to an aspect that I mentioned when I discussed the features of Wannier90, and I think this is really particularly relevant for this workshop. So Wannier interpolation is probably as I said, the most common application of Wannier functions in at least for for periodic solids. But while this might be considered an option, if you want, for some simple PVE calculation or a particularly efficient way to do things, it becomes, I would say, almost necessary, or at least a very recommended strategy when you go to beyond DFT methods. So to things like hybrid functional, for instance, the HSC or B3LEAP, or the PV0 functional, Koopman's compliant functional, as of those are the things that will be discussed on Friday, and also many body perturbation theory, in particular the GW method has been just mentioned in the talk of Andrea Ferretti, but is a very popular way of producing first principle band structures, okay, with high accuracy. And let's see why. I mean, in plain DFT, and by plain DFT, I mean really semi-local functional, like can be LDA or PVE, the potential is a function of the charge density only, no? That's what DFT is all about. So the Hamiltonian can be easily diagonalized at any arbitrary k point, this is exactly what you do. You don't even think about it. When you do a band structure calculation, Quantum Espresso, you have your charge density, you use it, you specify the number of k points, and you diagonalize on all these k points your Hamiltonian, okay? And that's how you do it. But if as soon as you move beyond plane DFT, and this can be, Hartree-Fock, it can be hybrid function, it can be GW, it can be different things, that's not true anymore. So you cannot do it. The key point where you want to calculate your eigenvalues needs to be part of the grid. And if you do hybrids, it needs to be part of the grid that you have to compute the total energy. Or if you do GW, many-body perturbation theory in general, it needs to be part of the grid that you use to compute the self-energy, okay? There are different ways to go, around this problem, but they all, in a way or the other, are essentially interpolation methods, okay? So if you want to do band structures with this, more advanced techniques, in practice, you can only do it through interpolation, okay? And one of, I think, probably the most physical and also the most efficient way to do interpolation for these techniques is Wannier interpolation. Actually, this is an example that I produced to explain this concept some years ago for GW. Okay, this is a G00 band structure interpolated with Wannier functions, and you see if you were to do an accurate band structure calculation, a G0 W0 calculation for this material, this is tungsten disulfide monolayer tungsten disulfide, you will need something like a 48 by 48 grid. Okay, so all these red dots come from a 48 by 48 grid. But instead, you can use Wannier interpolation and calculate quasi-particle correction only on a small coarse grid, in this case, a 6 by 6 grid that corresponds to the black dots. And just by using those quasi-particle correction on these very few K points, you can interpolate the band structure, and that's the orange line that you see, which perfectly reproduces the red dots, okay? And if you want to get even more accuracy, maybe you can go to a 9 by 9 grid, okay? But definitely you don't need a 48 by 48 grid. And for instance, in the case of GW and YAML in particular, you also use symmetry. So this 6 by 6 grid actually corresponds to just 7 inequivalent K points. So you can really be extremely efficient in your very expensive many-body perturbation theory calculation and just calculate, very few correction to your band structure with GW or other methods, and unfold them to the full Boolean zone and get a very accurate interpolated set of bands. Okay, so how do you this is a bit more in more practical terms. This is the workflow. I will not discuss in full detail all of this, but just to give you a flavor of how you do it and point to a reference where you can find more details about this. So if you were to do a Wannier interpolation of GW, G0 with quantum espresso and YAML, you would not use the standard workflow for a DFT calculation, for a DFT interpolation. You will still do an NSCF, and all the steps to get to, to produce the overlap matrices, because at the G0 level, your wave function is still equal to the, your GW wave function is still exactly the same of the Kohn-Sham wave function, so you just update your eigenvalues. But you also need to do another NSCF calculation that is now done instead on the reducible Boolean zone, so you can exploit symmetries. And that needs to be, the grid needs to be sufficiently dense to converge as self-energy and do your GW calculation, that in this case we do with YAML, for instance. After you do your GW calculation and you have specified the number of quasi-particle correction that you want to calculate, this doesn't have to be actually the same grid of the same set of K points that you use to converge as self-energy. You write this eigenvalues to a file, by using a post-processing code of YAML, and in doing this, you unfold them to the full Boolean zone, okay? So you take these eigenvalues, and then you take the overlap matrices computed at DFT level, the eigenvalues from GW. You sort of reorder things to guarantee that everything is ordered in energy. This is just a technical aspect that is needed because of the way Wannier90 deals with matrices and states. And then you Wannierize the system, okay? And then you get your GW level band structure interpolated with very, very dense sampling. If you want to know more about this, we will not discuss it today, but you can go on the Wannier90 code and look at example number 23, and there you find all the steps and explanation. And there is a tutorial that explains how to calculate G00 Wannier interpolated band structure for silicon. And finally, if you instead are interested more in hybrid function, this is what has been discussed earlier this afternoon by Yuri, I think, and Nicola Colonna. it's much simpler than that. So you do an NSCF calculation with a hybrid function. There is no NSCF calculation. You don't do an NSCF with hybrids. Again, we said that that's exactly why we need, there is a problem with that, because it's not a sole function of the density. But what you can do is you can use a code that is part of the quantum espresso distribution. It's called Open Grid, and it has been developed by Lorenzo Paolato, to unfold your eigenvalues and eigenfunctions from the reducible Brillouin zone to the full Brillouin zone, okay? And after that, you proceed as in a regular DFT calculation. We do run Wannier90 as a preprocessor. You get the input file for PW to Wannier90, you run PW to Wannier90, and then finally Wannier90, okay? So you only need to, to remind yourself that you don't have to do the NSCF. You cannot do that. You just need to unfold your SCF corrections, sorry, your SCF eigenvalues to the full grid. And of course, if you want to calculate empty bands, your SCF needs to include empty bands. But again, for this kind of workflow, there is a very nice tutorial on the Quantum Espresso repository. So it's part of the Quantum Espresso GitLab page that you find here below at the bottom of the slide, okay? So that was more or less what I wanted to say. So today, Junfeng will run the tutorial, and you can ask questions to Junfeng or me, and especially you will ask questions to the Slack channel, and then in some cases we'll read them loud, and otherwise we will answer them directly in the chat. From tomorrow, after this workshop, if you have questions and want to know, have doubts and want to learn how to get Wannier functions and do Wannier interpolation, you can start from the user guide, as I mentioned, the tutorials with the solutions you find on the Wannier.org website. You can register to the Wannier90 mailing list. And also, and this is something that I really want to recommend, actually read the source code, because Wannier90 is not a very complex code as it might be Quantum Espresso, for instance. Okay, it's much, I would say, simpler. So sometimes it's really, really very useful to just, look at the code. And if you have a doubt, let's say you want to know a little bit better how interpolation works. Sometimes the best thing is to go to the interpolation routine, just look at it. And often that tells you a lot more than you would think. And with this, I thank you for attention. I'm open to take questions.
Thank you, Antimo, for the great talk. So I don't see Andrea, so maybe I can pick a couple of questions for the Slack channel and report it to you. So one of the questions was, when do we need symmetry adapted Wannier? When would we have a code where symmetry adapted Wannier also support disentanglement? This is a question by Bani Chatterjee. Hope I pronounced it correct.
Okay, so that's a very good question, actually. So I would not say that you, in general, need symmetry adaptive Wannier function. Let's say, in most cases, it's you might want to do it, but it's not that there are many cases where you absolutely need. There are, I think, two different scenarios. One is where you are particularly interested in having symmetrized Wannier function. It can be, for instance, because you want to build a specific model, extract an effective model, or you want to reproduce to enforce a certain degeneracy that might not appear if you do maximally localized Wannier functions. I think one of the most, let's say, broad application of symmetry adaptive Wannier function is dynamic and infinite theory, okay, where they use Wannier function as a basis to perform DMFT calculation. There, I think that community really wants symmetric wave functions, and they enforce symmetries, okay? And this is, I think, part of the answer. The other aspect is that there's not let's say, a unique way to calculate symmetry adaptive Wannier function. There are different approaches. There is the real symmetry adaptive Wannier function. There are the selectively localized Wannier function with constraint centers, and some of them have more or less functionality. I think in some cases, as the participant correctly said, you cannot use disentanglement. In other cases, you can. So depending on which specific, let's say, flavor of symmetry adaptive Wannier function you refer to, and then the fact that this entanglement will be included for those techniques depends on the developers of those features if they plan to work on it or not. I think that there is some work going on in that sense, but I don't know more than that.
Okay, thank you very much. So in the interest of time, I think we go to the hands-on session, and then we'll try to reply to the other question directly on Slack. Thank you very much. Very great talk. So yes, now it's Yunfeng is gonna run the
Okay, thank you, Nicola, and thanks, Antimo, for the great introduction. So now I'm going to present how to run some practical Wannier90 calculations. So let me share my screen. Okay, can you see the virtual machine?
Yes, we can.
Okay, perfect. So today we're going to run 2 tutorials instead of 3. So I delete the valence case of the silicon, but if you are interested, you can find the corresponding tutorials in the Wannier90 repository. So today we're going to first run a Wannierize the valence plus conduction band of silicon, and then we will try to do this Wannier interpolation for the Fermi surface of lead. So if you haven't downloaded this tutorial, you can go to this GitHub repo and then git clone the repository. So we will also use 2 codes to plot the band structure. The first is this GNU plot, and then this XMGrace. For these Wannier functions or the Fermi surface, we will use this XCrystal, and these are already pre-installed in Quantum Mobile. So let's first start with this silicon case. So the exercise is in this exercise 5. So we go to this folder, and now you can see there are some templates for the input file. So if we open this first one, this is for the SAF calculation. So as you can see, we run a self-consistent calculation and the pseudopotential and define these atoms and the coordinates, and also use a 10 by 10 by 10 K-mesh. So we have several different ways to visualize the input file. So for example, we can use this QE input generator. So we open this URL, and you can upload the input file. That is to upload this 01 SDF. Okay, let me try browse. Okay, it's here. And now you can double click and to rotate the structure. So also it will suggest several convergence parameters and like the K-mesh for you, and it's a good reference for you to run an actually converged calculation. And now we also have this XCrystal. You can run this directly in terminal, XCrystal --pwi, and the file name of this input file. And now we can also have a look at the crystal structure. So there are several questions here, like just ask you to check the number of electrons in this pseudopotential to let you understand how many number of bands and number of Wannier functions you should use if you want to Wannierize only the valence band. But I'll let you do this as a homework. So now we are going to run this calculation. So we will run with 2 processors with this input file, and then we will redirect the output into an output file. Okay, there's some warnings, but we can just ignore it for now. So let's first have a look at the output file. So let's just ignore this stuff. So now we start our PWSF calculation and some parameters. And you see we have some convergence here. Now it's converged. And after you check that everything works fine, we can proceed with the next step. So the next step is to compute the band structure, the quantum espresso band structure. So actually we can make a new folder called bands. And then we copy the previous input file and also the self-consistent charge density file here. This -r means we copy the folder. And now we need to change a bit the pseudopotential directory. And we change this self-consistent to bands calculation. Okay. And we need to, we want to compute 12 bands. So we have to add this NBND in the system name list. And actually, if you want to converge also the conduction band, it's better to set this tag in this electron. You can find more explanation in the documentation of the pw.x. So we also need, since we want to compute the band structure along a path, so we need to change the K points. Crystal. And then we just copy paste this one. So these are the K points coordinates of high symmetry points. And now we are going to run this calculation. I'm going to rename the file. And we're going to launch this calculation. Also, you can use this T command to output the calculation and also save it in this bands.out file. Okay. Okay, I forgot to put this too. So because it computes like hundreds of K points, so it will take some time. Okay. So as you can see, the job finished successfully. And to plot the band structure, we need to run some additional executable that is provided by the quantum espresso. So specifically, this bands.x for the input file for the bands.x. So I'm going to move this file into the bands folder. And let's try to edit this file. Yeah, it seems fine. So you can use this command to run this bands.x. And again, I'm going to use this T command. Okay, so the calculation now finished and it generates some data file that contains the eigenvalues for the band structure. So if you want to generate a graph, a figure from this data, you can run this plotband.x code. So it's a interactive code. So it will ask you to provide the input file. So here we use the file generated by the previous step. And it will ask you to provide the y-axis range the energy range. So I'll just use the default one. And also the file name for these some output file, we'll name it as this. And the output file for the figure, which we will use this QE_bands.ps. And the Fermi energy. So in principle, you should find the Fermi energy from the self-consistent calculation.
Sorry, Junfeng. Some participants say that you go a little bit too fast.
Okay.
Yeah, thanks.
So okay, I'll try to slow down. So we need to find the Fermi energy from the self-consistent calculation. So which you can find from the output file of this one. So you can find, since we are having an insulator, so it will output the highest occupied level. So this one. So we copy this file, copy this number here, and paste it here. And here, this delta E means the distance, it's just like, let's try to use 1. So that means the tick on the y-axis has 1 as the smallest unit. And the reference E means we can use this Fermi energy. So then this will shift the energy, the y-axis. So now the Fermi energy is 0. Okay, so we have this file. We can open it. If you like, you can use these files to open this figure. So let's go to this one. And now we have this PS file, which is just the figure for the band structure. But it's like we have to rotate it. So here, we can rotate it with this one, right? Okay. So as you can see, this is the silicon band structure. So now the Fermi energy is shifted to 0. Okay. So now these are the steps for computing a quantum espresso band structure. But now we are going to compute the Wannier functions and use Wannier interpolation to compare the band structures with respect to quantum espresso. So we need to first run a non-self-consistent calculation on a regular grid, and then we will run this PW to Wannier90 to generate the essential files, that is the projection matrices and also the overlap matrices. And then we can run Wannier90 to generate the Wannier functions. So to do this, we need to prepare a non-self-consistent input file. So we still copy the previous file from the bands calculation, the second one. So let's name it as 5. And we will change this calculation to non-self-consistent. And also remember, we have to change the pseudo path. Also, we need to run this on a regular grid. So now we have to change the K points. For this Wannier90 provides you a very simple script that is called this K-mesh-PL that can generate a regular grid for you. So actually it's located here. It's a bit long. So to save our time, we can use this command, which will add this path to this path variable. So that means in the following, if you want to execute this command, you don't need to type all these full paths. You can just use this kmesh.pl to run this code. So let's copy this line. and paste it here. No. Copy. Okay. So if you want to have a look at this path variable, you can use this command, echo, with a $sign. So as you can see, we just add this path to this variable. So now if you type kmesh.pl, you can see we can just exit this code without the full path. So for example, this code, like if we type 2 by 2 by 2, so this will generate a 2 by 2 by 2 grid and its coordinates and its weights that you can just directly copy and paste in the Quantum Espresso input file. But here we're going to use a 4 by 4 by 4 mesh. So we change this to 4 by 4 and by 4. It's a bit long, but we're going to copy this. Copy. And we added these non-self-consistent calculation. So we first delete the old one and then just paste the new coordinates. Okay. And also we have to delete the previous crystal B, which is just for band calculation. Okay, so the input file is ready. We will compute 12 bands. So again, we use this MPR run command with 2 processors to run this non-self-consistent calculation and save the output file to nsf.out. So since there are like 4 cube, that is 64 bands, 64 key points. So it will take a bit, some time, but okay, so it's now finished. So everything works fine, as you can see. So now we're going to prepare the input file for Wannier90. So all these Wannier90 will read this win input file. So the name will end with .win. So we open this file. And I leave these XXX on purpose. So you need to edit this yourself. Otherwise you can't run it. The code will complain that there's something wrong with the input file. So the first line is use WS distance, which is just as Antimo said. So this is using the minimum distance selection method that you can find more explanation from the user guide, which just essentially just has a better interpolation quality. So what we have to edit is this number of bands. Since we use 12 bands in the non-self-consistent calculation, so here we have to type 12. For number Wannier functions, since we're going to Wannierize the valence and the conduction band together, so for a silicon, this structure, we have 2 silicon, and on each silicon, we use this sp3 projection. So each silicon has 4 orbitals. So with 2 silicon, we have in total 8 Wannier functions. So we need to type 8. And also we use 100 step of maximum localization. Since we're going to Wannierize the valence and the conduction, so we need to invoke this disentanglement procedure. So we need to set this window max, which is the upper bound of the disentanglement range. So usually you need to make sure it is large enough to include all the relevant states that you want. So here we have some, I already tested, so we can use this 17 as this value, but in principle, if you want to Wannierize your own structure, you need to look at the band structure and understand which part of band is relevant for your purpose. And then for the frozen window, so below this frozen window, all the states are freezed. That means the band structure will be exactly reproduced. So here we're going to freeze all these valence band. So from this Fermi energy, or the highest occupied level, we copy this number and paste it here. Oh, paste it here. Copy. Paste. And we will also run 100 steps of disentanglement. So we will plot the Wannier functions, so you can visualize it with XCrystal or other tools. And this is the supercell, the size of the supercell that you will use to plot the Wannier function. And also we want to have a look at the interpolated band structure. So this is the band plot should be true. And then we tell Wannier90 to compute the band structure along this path. So these are the projections that you have to try and guess according to your chemical intuition. So here we know this silicon has sp3 orbital is a valid initial projection. So here we just use sp3, but in principle, you can also use sp like s and p, for example, using this one. So it will project to s and p orbitals for our Wannier functions. You can try it and have a look at the results. But here I'm going to use sp3. And here is the coordinates for this silicon atom. And then this unit cell. And here we need to ensure we have the same grade as the non-self-consistent step. So it's 4 by 4 by 4. And we need to change to also input the coordinates. So for this, we can again run this kmesh.pl. So 4 by 4 by 4. But if you run just 4 by 4 by 4, it will also output these weights of the K points. So if you add this 1, it will not output the weights. So we can copy this one to the input file of this Wannier90. Copy. And paste it. Okay, so it's an extra line. I will just delete this. So now we have prepared all this input file. So the next step is to generate the NNKP file, which is the input file for the PW21 to Wannier90 step. So for this one, we need to actually these are some detailed explanation of what I just did. So if you didn't follow, you can reread these lines and help you understand these input tag. And especially you should also look at this user guide to understand in more detail the meaning of each parameter. So now we're going to generate this NNKP file. So for this one, we run Wannier90.txt, but with this extra command, this -pp. So it will finish in seconds. And now here's the output file for Wannier90. Let's have a look. So this is our first Wannier90 run. So here are some headers. And our structure, the lattice vector, the reciprocal lattice vector, the atom coordinates, the K grid, and some parameters we use for the convergence, etc. And here, this is for finding the B vectors, which you will have which you can find some more explanations from the paper of this review of modern physics or Nicola's paper. But let's have a look at here. So the Wannier90 code tries to find some essential information for computing these overlap matrices. And now it writes this information to this NNKP file. So you don't need to care about the details here, but essentially you should need to make sure this run is successful and it can successfully generate this NNKP file. So with this file and also the wave functions in this out folder, it's saved. This is the quantum espresso wave functions here, and also the charge density. So with this wave function and this essential information, we can now launch this PW to Wannier90 code. So this will write these overlap and the initial projection matrices. So again, we need to prepare an input file for this PW1. So actually it is here, is the sixth input file. So this is rather simple. We first specify the output file for these wave functions, and then the prefix of the quantum espresso calculation. And here the seed name must be the same as this input file. So this silicon2, ISI2. And now we ask the code to write the initial projection matrices and also these overlap matrices. So the first initial projection is called AMN file, and then the second one is the MMN file. And we also ask the code to write the wave function. It's called UNK file. So with this UNK file, we can plot the Wannier functions in real space. So let's try to run this calculation. So now we're going to use another executable called PW2 Wannier90 and the input file, and save the output to this file. It will take some time to compute the initial projection. And these overlap matrices, that is here, the M matrices, the A is for initial projection. And there are some other matrices, other files that's for example, computing the orbital magnetization or spin Hall conductivity, but we're not going to compute such physical properties. So we're only going to write these files, the wave functions files for visualizing the Wannier function. So now, as you can see, we have several additional files. The first one is this ag file, which is just the eigenvalue of these. So the eigenvalues on the regular mesh, that is 4x4x4, and then we can have a look at this one. It's pretty simple. It's pretty simple. Just a list of these numbers. Actually, you can find the exact specification of this file in this user guide, but actually here is just, you can see these are 12 bands we're going to use. And the second column is just the K point. So you can see there are 64 K points, and then these are just the eigenvalues, the energies. And we have this MMN file, which is for the overlap matrices. It's a bit larger, but it's just a bunch of numbers for the matrices. And we also have this UNK file, which you cannot edit because it's binary, to save the disk space, because this our wave function is quite large. So we can run this command to have a look at its size. This is in bytes, but if you add this H, you see it's 2.6 megabytes and 64 K points. So in total, it's quite large compared to these small matrices. So now we are going to Wannierize our first silicon valence and conduction bands. So it's pretty simple. We can run still with MPI, 2 cores, Wannier90.x. And then, so actually in Wannier90 language, so we call this SI2, the seed name, as you can see from this BW21 input file, is called the seed name. So the seed name is just the name before the dot of this win file. So this is the extension is .win. So this one is the seed name. So as you can see, all these files are started with this silicon tool. So now we run this Wannier90, Wannier90.x. So with the seed name, or if you want, you can also type this .win, but you can just use the seed name and it will automatically add this .win file to find the corresponding input file. So we're going to also use 2 cores and run the calculation. So here there will be no output, but it will write all the output to a wout file. It haven't finished. But here, this is the output. You can have a look at this output. So as you can see, the calculation is still running. So these are just the headers, the previous header. So we will skip this, the headers. But here, as you can see, we first read the overlap matrices, read the initial projection matrices, and read our specified energy windows for disentanglement. And then the code starts to do this disentanglement process, which ends with these Ds. So we start the omega I, that is the gauge invariant part of this spread functional. It's gradually decreased, and this is the convergence. You can find that it converges to under 10 to minus 10. And okay, so the calculation finished. And then the second step is Wannierize. I need to reopen this file. Let's reopen it. So let's go to the Wannierize. Okay. So these are the new output. So now this step is the maximum localization. So as you can see, first we do the disentanglement and then do the maximum localization. So we have 8 Wannier functions. As you can see, we use SP3 initial projections. So the initial projection are really 4 symmetrical SP3, and then another group of SP3. But their spreads are symmetrical. And here, these are the Wannier centers, the center of these Wannier functions. And here, these are the sum of the center and the sum of the spread. So we're going to look at this convergence trend. So here, we're trying to see if this is converged or not. So the delta means the difference between this step to the previous step. So here is around 0.4. So the algorithm tries to minimize this spread functional. So it's decreasing from 18 to 17. And decreasing is the same just during the iteration. And after 100 steps, so it converges to 10 to minus 13. So this is pretty well converged. So these are our final spread for final Wannier functions. And then the code will compute the real space Wannier function. So as you can see, this is the maximum imaginary to real ratio, which is a good signature of the quality of your Wannier function. So if you get a really small number here, that means you get real valued Wannier function. That means they are not complex numbers. So this means that its quality is often quite high. And then this also compute the band structure. So finally, the code ends. So it takes 21 seconds. for this plotting, and also just 1 second for this Wannierization and 0.3 second for disentanglement. Okay, so now there are several different files. So especially this silicon-2 bands file are the band structure, the Wannier interpolated band structure, just the eigenvalues. You see, this is just the K points and the eigenvalues, just some array. And also there's the GNU file, which is this GNU script, GNU plot script for you to visualize the interpolated band. You can run this GNU plot, and with a -p, that means we keep the GNU plot window there instead of exit immediately. So here, this is the Wannier interpolated band structure. It's pretty smooth. So for example, if you didn't forget to add this -p, the GNU plot will just plot and immediately exit. So you have to use this one to make sure it's keep the window there. Okay. So we're going to compare the Wannier interpolated bands with quantum espresso bands to make sure we really reproduce the quantum espresso band structure. So for this one, we can use this line. We copy this, just some GNU script, GNU plot script. We name it as the diff or something, anything you want. And we paste it. So the script, essentially, these are set this output format, like the range, the y-axis range, the x-axis range. And also it will first read the bands.data.gnu. But remember, we run calculations in a different folder. So we need to change a bit here. And then this silicon-2 bands.data is just the Wannier interpolated bands. So again, we use GNU Cloud to run this script. So these are these Wannier interpolated bands. So as you can see, the valence band are very well reproduced, and the conduction band is. So we set this Frost window, the frozen window here at the Fermi energy. That means all these underlying bands below this frozen window will be freezed. So they should be exactly reproduced. But here, above the Frost max, it's not guaranteed that they will be reproduced. But in our case, it is also reproduced nicely. So this is our first comparison of the quantum espresso with the Wannier90 bands. So if you want to try some other software for comparing band structure, there's also this XMGrid. You can try to run this command to also compare band structure, but essentially they are the same thing. So now we're going to visualize the real space Wannier function. So also from this UNK file, the Wannier90 compute these, and also together with the unitary transformation matrices, the Wannier90 compute this XSF file, which we can visualize with X Kristen with --XSF and the file name 1. So we have to use this one, data grid. So this is written here. So you choose data grid and OK, and then choose some ISO value for the surface you want to visualize. So I'll just try some numbers. So here is the minimum and the maximum value. So you should try some value between this minimum and maximum. So I'm going to use 0.5. And also we render the plus and minus surface and we submit. Okay, so these are the Wannier functions, the first Wannier function. you can also change the SO surface, and of course it will be different. And also we can try this with other file. And again with this data grid. 0.6, try a different value. So you see this the Wannier function along a different direction. You can visualize your Wannier functions and understand what are the characters of these orbitals. So if you try to use the different projection like S and P, and then you try to redo everything and you see the difference, what are the Wannier functions you generated? So there's some optional homework for you. So you can try like, so here we use SMP, SP3, you can try with different projections. And also here we use a rather coarse K-mesh, that is 4 by 4 by 4. You can try to increase the K-mesh and see the difference. And also you can play with the frozen window to understand the effect of these parameters on your Wannier functions. So this is the first exercise. So in summary, we run this SDF calculation and then the band structure calculation fully inside quantum espresso. And then we compute these non-self-consistent calculation to prepare wave functions on a regular grid. And then we prepare the input file for this Wannier90, which generate the NNKP file for the PW to Wannier90 calculation. And then we use PW to Wannier90 to compute the AMN and MMN and the ACK file. And the last step is to run Wannier90 again on this Win file. So it Wannierize the system and compute the band structure and also generate these real space Wannier functions. So this is the first exercise. So it's already 6 o'clock. I don't know if I should.
Yeah, Jay, exactly. Frank, thanks a lot for the great tutorial.
Yeah.
I was discussing with Nicola Colonna, Yuri, and Andrea, and the others. So in the interest of time, we would stop here with the tutorial. So I think you did a great job in explaining what I called exercise 1 and 2, and that were compressed in the Seina, what you called exercise number 1, and what we used to call exercise number 3, which is the lead Fermi surface and band structure. I think we can leave for people to carry on at home. I think the PDF contains a lot of detailed information with all the steps. So it can be run by each of you autonomously. So it should be detailed enough. So Nicola Colonna suggested that it would be instead a good moment to take questions, right, Nicola?
Yeah, yes. Maybe if there are some questions, we can take 1 or 2, and then we let everybody go.
Maybe I can. So I've seen a couple of different general questions appearing throughout during the talk or during the tutorial of Junfeng. I try to answer them in the chat. So maybe I can sort of give a general answer here. So some people ask me, should my Wannier band structure exactly match the DFT calculation? No? Well, I mean, it depends a little bit what's your purpose here, okay? So in the context, I think of the number of things we want to do in this workshop, like interpolating band structures with relatively more or less advanced methods ranging from DFT to Koopman functional or hybrid functional or plus U. I mean, in general, you want them to be very accurate. So you want them to match exactly what would be the direct calculation, and of course you want them to do that in the energy range that you're interested in. It can be certain number of electron volts around the Fermi level. It can be more, depending where are you studying your band structure. Now, it's a different story because some people mentioned works they found in literature. It's a different story if you want to use Wannier interpolation to do other things, like to extract specific small type-binding models that describe specific bands. And some of this has been introduced also by Giovanni earlier on when he showed, the S bands isolated bands that you interpolate. It can be in copper or other simple metals. But in general, it's another way of using Wannier interpolation. You extract, let's say, a two-band model that can, let's say, describe graphene around the Fermi level, or, in different case, the s orbitals in gold. It can be different things. But in that specific case, of course, the bands deviate a lot outside the region of interest. But in general, if you're just interested in interpolation, of course, I mean, that's the whole point of the Wannierization. You need to reproduce accurately the band structure. Otherwise, it means that the Wannierization is not performed correctly. This is, I think, a question I saw multiple times, or at least in different flavors. Other general questions? Yeah, for the projections, I mean, we mentioned the SCDM as an alternative, where you just try this linear algebra-based approach, where you don't think too much about the orbitals and the chemistry. But a very good strategy is always to do a projected MCO state of your system. Okay, so you look in the energy range where you want to study your band structure. You look at what are the atomic orbitals or the hybrid orbitals where your band structure projects most on. Okay, it can be mostly s orbital, sp3 orbitals, and so on. And actually, what this very recent method that Giovanni has mentioned has been a work done mostly by Junfeng, where they even went beyond SCDM with this projectability based approach. Is essentially a way to automate that strategy. So you look at you take your eigenstates, you see how much they project on all your atomic orbitals, and based on that, you build your projections, your energy windows. And a similar approach, although in a different framework, has been done by other groups with this so-called PAO. So I think it's called projected atomic orbitals approach. So let's say projected MCO states, I think, is always a good starting point if you want to understand a bit how to Wannierize a system.